So first, a very quick overview of the uh, anatomy of the eye. Right, the eye is made up of a cornea, which is the front of the eye, which acts as a lens in itself because it is a curved surface, and that has kind of a fixed shape, and so it's got a fixed amount of power, and then a variable lens called the crystalline lens that is controlled by the ciliary muscles, which are connected by fibers to the crystalline lens. When the ciliary muscles relax, the crystalline lens flattens itself out. On the other hand, when the ciliary muscles are contracted, which takes some effort, the crystalline lens takes on a more rounded shape. Turns out that when the lens is in its most relaxed shape, that's this flattened shape, the combined lenses of the eye have a focal length that is appropriate for viewing distant objects. On the other hand, when the ciliary muscles contract and provide a more rounded lens shape, that turns out to give a focal length for this combined lens that is appropriate for viewing objects up close. And this process of controlling the shape of the lens so that we can focus on objects from very far away to very close is called accommodation. So taking that diagram of the eye and making it much more simplistic, we can view the eye as a sphere with a retina at the back end, and that is where we want to form our sharp image. And we'll treat the combined lens of the cornea and crystalline lens as a single lens right here. One important number to know is that the human eye separation between the lens and the retina is approximately 20 millimeters, or 2 centimeters, and that's very typical for a normal human eye. So let's imagine we are looking at something that's very, very far away. A very distant object is going to have light rays that are coming in nearly parallel to the optical axis. And the goal is to take those parallel rays and bend them so that they all come to a focus 20 millimeters behind the lens at the retina. That's going to require a certain shape of lens. Let's compare how the shape would have to change in order to see something more close up. If the object is brought in closer and closer, then it turns out what we need is a more rounded shaped lens than we needed for focusing on something very far away. And the reason you can see this is because compared to the distant image, we now have light rays that are coming at us with a fair amount of divergence. And we still want to cause those rays to come and make a sharp focus that same 20 millimeters back, which means we have to do a lot more bending of the ray. And that's going to require a more rounded shaped lens. So let's take a quick aside away from the eye and just make sure we understand that that's the case. If we take a piece of glass that has no curvature at all, right, and we send parallel rays through it, they won't focus at all, right, and that will cause no focusing. So no curvature is associated with no focusing. On the other hand, if we take a very high curvature lens, like a marble effectively, and we send light, again, coming in parallel to the optical axis from a distant object, we would take each ray and trace it through the air to glass and the glass to air interface using Snell's law. And the net effect is to have quite a bit of bending of the light as it passes through the lens. And clearly an intermediate case would cause weak focusing or mild focusing for a mild curvature. So the more curved the surface of the lens is, the more it will bend light, and for a positive lens, that will cause the light to converge more strongly. Right, so now we go back to the picture of our eye and we see that if we need this same lens to take light that is diverging and converge it to the same spot, then it needs to converge those rays even more strongly, which is going to require a more rounded shape. For the purpose of brevity, we will often refer to this normal eye that has a lens to retina separation of 20 millimeters as simply an eyeball of 20 millimeter diameter. So for an object at infinity to be focused at the retina at the back of a 20 millimeter diameter eyeball requires a lens with a focal length of 20 millimeters, because we know by the definition of a focal point or a focal length that collimated light from very, very far away will be bent by a positive lens and come to a focus one focal length behind the lens. Now let's consider the case of viewing more nearby objects. For a normal healthy eye for a young person, the healthy near point is about 250 millimeters, and that's about as close as you can get and still really sharply focus. If we place an object at this near point at 250 millimeters in front of the eye, that object to be focused to the retina at the back of a 20 millimeter diameter eye requires a lens with a focal length of 18.5 millimeters. And you can figure this out by taking 1 over p, 250 millimeters, plus 1 over q, 20 millimeters, is equal to 1 over f. And you get 18.5 millimeters for the focal length of the eye when viewing an object at 250 millimeters away. So now let's consider different cases where the eye does not see properly, right? Specifically, nearsightedness and farsightedness. So let's start with nearsightedness, or what's called myopia. Notice that in a myopic eye, as we've drawn it here, the problem is that the light from a distant object focuses too early in front of the eye. Okay. So what's happening here is you've already relaxed the eye as much as you can. This is the longest focal length lens that your eye is able to produce, but that lens is not quite flat enough. A person who suffers from nearsightedness can focus on nearby objects, but cannot bring these distant objects into a sharp focus on the retina. That is to say, in its most relaxed state, the lens is not flat enough, as we just said. Or another way to phrase it, their longest focal length lens, this most relaxed lens, has a focal length that's still not quite long enough, or a focal length that's too short. So in myopic eye, the lens is too curved for the length of the eyeball. It's just not flat enough. Or stated another way, the eyeball is too long for the relaxed lens. Right? If this is as relaxed as the lens can get, you really wanted the retina to be right here. And so the eyeball is considered to be too long for this relaxed lens. So how do we fix that? Well, qualitatively, you can see that the solution is to cause the light rays to focus further back at the retina, right? Because since we can't change how big your eyeball is, and we can't change the limiting shape of your eye without going in and doing surgery, what we want to do is we want to diverge the rays slightly so that they end up focusing further back. So what we want to do is we want to insert a diverging or negative lens in front of the eye. Quantitatively, if we want to figure out what prescription we need to fix a particular amount of myopia, we have to realize that what we really want is to take an object at infinity and produce an upright virtual image at the far point of the myopic eye. That is, we have an object way out here in infinity. You can imagine a big glowing arrow out here. And what this negative lens wants to do is to produce a virtual image of that object right here, the uncorrected far point of this eye. The uncorrected far point of the myopic eye is the furthest distance at which the person can see clearly without glasses. So for a person with normal vision, they can see very, very distant objects, and the uncorrected far point can be out at infinity. But for a person who has myopia, they can't see very far away. The furthest distance that they can see clearly, can get a sharp image, is the uncorrected far point. And if that's the furthest out they can see, then what you want to do is you want to take the object that's way out here in infinity and make an image of it at the point where they can see clearly. So let's do an example. For a person who has a far point of 0.3 meters, meaning if you have somebody who's nearsighted and they take their glasses off, they can not read, or at least not clearly read, a page that's more than a third of a meter out in front of their face. And then our lens equation says 1 over f is equal to 1 over p plus 1 over q. Right? And we want to know what the focal length of the corrective lens is that will give us take a distant object, so p is equal to infinity, and produce a virtual image 0.3 meters in front of the eye. And remember, because we think of the normal standard case of imaging as an object on this side and an image on the other side of the lens, when the image is meant to show up on the left side, that's a negative image distance, and hence comes in with a minus sign, right? So virtual images with lenses come in with this minus sign. And we want it to be 0.3 meters, so it's going to be 1 over minus 0.3 meters. If we do the math, this is just 0. Right? 1 over infinity is 0. And 1 over minus 0.3 is minus 3.33 inverse meters. We take 1 over that to get the focal length, and it turns out we need a minus 0.3 meter focal length lens, or a 30 centimeter negative lens. Now in optometry, lens power is stated not in focal lengths, but in this thing called diopters, which is just 1 over the focal length. So that's this. 1 over the focal length is 3.33 inverse meters. Inverse meters is called diopters when you're talking about corrective lenses. Right? So the prescription for this person would be a minus 3.33 diopter corrective lens. All right, well, we can do the same analysis for farsightedness or hyperopia. Notice that as we've drawn up here, that what happens with a hyperopic eye is that light from a nearby object ends up focusing too far back behind the retina. That is, a person who suffers from farsightedness can focus on faraway objects, but they cannot bring nearby objects into a sharp focus on the retina. But even in its most strained, most rounded shape, the lens is still not curved enough to view nearby objects. Or we could think of that as the shortest focal length available to this accommodated eye is still not short enough, or the focal length is too long. So in a hyperopic eye, the most rounded shape that the eye can produce is still too flat for the length of the eyeball. Or another way to think about it is that the eyeball is too short for this most relaxed lens. So to fix this, qualitatively, the solution is to cause the light rays to focus closer in. We want it to converge more. Then what we want to do is place a positive lens in front of the eye. Now looking at it quantitatively, what we want is to have a lens that will take an object that is at the typical near point, right? We say, this is really where I want to be able to put the paper so that I can read it, right? But I can't focus that close in. I can only focus to my near point, which turns out to be further away. The uncorrected near point, which should be 25 centimeters for a normal eye, for an eye with hyperopia or farsighted person, that uncorrected near point is actually further out. And by definition, that uncorrected near point is the closest distance at which that person can see clearly without glasses. So taking an example, if a person has a near point of 40 centimeters instead of the normal 25 centimeters, then the corrective lens that we want is one that brings the object placed at 25 centimeters, which is too close for him to read, and make an image of it at 40 centimeters, which is far enough away for her eye to come bring it into a sharp focus. Right, so the focal length we need is one that takes an object at 0.25 meters and produces an image at minus 0.4 meters. The minus sign is again because for a lens, image space is negative when it's on the same side. We do the math and we turns out that gives us a 1 over f of 1.5 inverse meters, which makes the focal length a 0.667 meter focal length lens. And again, in optometry, lens power is stated in diopters, which is 1 over the focal length, which is just this number, right? So this person would require a positive 1.5 diopter corrective lens, right? And that's it.